3738. All right, good afternoon. So we'll pick up where we left yesterday. But before I start, we'll go over some of the questions you guys had. I don't know if everybody who asked the questions is there today or not. So let's go back. Okay, just to remind what we did. Yesterday, we make it slightly bigger. We talked about different distances. We talked about the general Minkowski distance, which is the P norm, Euclidean, Manhattan, Chebyshev. I told you to look it up. Did everybody looked it up, the homework? No, yes? Check it out. And then we talked about the Hamming distance. And then we were at this slide where you guys were getting a little confused. So we'll go over that. Then what we did was we said we worked out a theorem to find an exemplar which says if you're finding the squared distance sum of squared from a point, then that point will be the arithmetic mean. We proved that. And then we had to start the centroid and medioid. So before I start that, we'll go over this slide again. So J is lecture 11 and okay. So we're just recalling, है ना? So recalling. So this everybody got that. How did we got circles? Let me not open this slide. Then you will get confused. Let's an empty slide. So everybody got how we got the circles, right? Minkowski distance. If you're finding distance between 2 points x comma y, it was, let's write this. So summation of norm of xj minus yj, they're using j rather than I, and j going from 1 to d. D is the number of dimensions and to the power 1 over p. Okay, so this is what we were doing. So so p equal to 0 is a special case, which is the Manhattan distance, or we can start from the larger values. We'll just start from the larger values and we'll go backwards that way. So if we were doing p is equal to infinity, correct? Then what was this distance? This was the maximum of xj minus yj. Basically the maximum component which you get, that is what the distance was. Then there'll be a case, for example, okay, what we did was we did p is equal to 2 first. So for p is equal to 2, we said that if the distance is x1 minus origin plus, or x and y are the two components, let's say, so there is y minus 0 square is equal to some distance c square, right? So we were getting this to be the circle of radius 1, and then if it is the distance was square root 2, that was getting a radius of 2. Correct? This is what we were doing, and then we had drawn and all that stuff. So the question which we were trying to answer was that, you know, if this was another circle of radius 1 and this was origin, this was A, this was C, this is radius 1, this is radius 2, so OA plus AC would be greater than OC, which would be probably greater than 1 and less than 2. This is what that is why it satisfies the triangle inequality, satisfies the 4 conditions, right? Then we came to P is equal to 1 case where we just said that x minus 0 plus y minus 0 is equal to C or 1 or 2, and then we said y absolute is equal to minus x plus C, and then we had drawn this. So there was a doubt which you had. What's your name? Shivam. Okay. So Shivam had a doubt which was valid, and I wanted to address that before I go ahead. So we had drawn that all points on this rotated square will have equal distance from the origin, right? Correct? Yes, Shivam? And then what we had done is we had drawn that this is equal distance to, and then if it was something was centered here, then this would be this, this, and this. And then we had to show that OCAC. We were saying OA plus AC is equal to OC, which was becoming 2. So the concern which he was asking was that if this is 2 and this is 2, then this A should lie on OC line. Basically, that's what you were saying, right? So the problem is that it's a Manhattan distance. So the Manhattan distance is not computed like a Euclidean straight line. It is, what happened to this? It is drawn in terms of the axis which you're going. So if I have to find OC, I would go here and go here. So what I will do is I will go this line and I will go this line. So although I'm showing it as a OC distance, but because it is a Manhattan distance, it will go along the axis. Does it make sense? If I am here at this point, I will not say that this is the distance. This is exactly still 2. This point is also exactly 2. But the distance, the way it is measured is, to measure this point, I would go this way and this way. So this will be probably, this whole thing is what distance 1 and this is distance 2, right? So this would be something like 1.5 and this will be 0.5. And if I'm going here, I will go this, which will be 0.5 and will go vertical 1.5. So in that sense, you're not exactly going a straight line. You're always going along the axis in the Manhattan distance. So we are not exactly saying this is 2. We're saying the distance between O and C is 2, which is measured along the axis. Make sense? Is it clear to everyone? Okay. And then what we did was, we did the case of P less than 1. In P less than 1, we said that it will become slightly curved lines, something like this, something like this. And then for this guy, it will go somewhere out, come out, go somewhere out, come out. And now if you see the OA and C, so OA plus AC would be less than OC, which is going outside the 2 radius. So it is not satisfying the triangle inequality. Is that okay? This is a summary of. Now coming to more questions. So more questions related to this is, so for example, if I had to draw between 2 points, so the cases which we have not seen is what if P is greater than 2. So if you have 2 points like this, and you have, let's say, these points, these were the points, this is the Euclidean distance. If P is getting lesser, then it is becoming a curve inside. If P is getting greater, then it's going an outside bound. So this is P is equal to 1, this is P is equal to 0.8, this is P is equal to 1.2. So this goes like that. Anything P greater than 2 is also a distance metric, although we don't prove it. So is a distance metric. What is the most problematic thing to prove it's a distance metric? The first 3 are straightforward. That it's with itself it's 0, with another point is greater than 0, it's commutative. OA is AB. The triangle inequality. So in this one, the triangle inequality does get satisfied, although for P less than, it does not get satisfied. Correct? So that's another thing. And last one was P is equal to infinity, which is the Chebyshev distance. So Chebyshev distance just measures the longest dimension. So if between these 2 points, this is the longest dimension, so this would be the Chebyshev distance, visually if you want to see. Is everybody clear? So as the P increases, the difference, the larger difference gets dominated. So another example, let's say if I have got 2 points 5 comma 2 and 7 comma 3. No, sorry, 3 comma 7, let's say 3 comma 7. Okay, so now which dimension? So if I have to find p is equal to less than 1, I'm ignoring because it's not even a distance metric, so I'll not even go there. If p is equal to 1, this difference will be 5 minus 3 plus 7 minus 2. Correct? Both the differences are given equal weightage. Hai na? When p is equal to 2, then it is 5 minus 3. देखना, it could be a spam अगर कुछ ऐसा हो तो 5 minus 3 square plus 7 minus 2 square. है ना? So which is the larger difference? This is 4 square and this is 2 square. So this starts dominating. When p is greater than 2, let's say it's 3. Again 5 minus 3 cube plus, of course there is over 1 over 1 over 1 over 2, and this is 7 minus 3 cube over 1 over 3. But which is dominating? This is 2 cube and this is 4 cube. This is dominating. So eventually when you go, कौन था? P is equal to infinity, then you just have the maximum dominating, that is 7 minus 3 absolute. So this becomes 4. Is that okay? So this is where you can visualize this, that as you increase the p, where the difference in the which dimension, of course I am doing 2-dimensional here. In real life you have many dimensions. Sorry, 7 minus 2, 2, 2. I don't know why I'm writing 3. 7 minus 2, 7 minus 2. So this is 5. 5 is dominating 5 square, 5 cube, and eventually it will be 5. I just randomly picked some value. But the point is, I'm showing you only for 2 dimensions. It could go for much larger dimensions, and then you will realize that the dimension where the difference is the largest starts to dominate your result. That is what it's trying to say. But in real life, what we'll do, we'll not worry about p less than 1 definitely, because it's not even a distance metric, correct? P is equal to 1 is commonly used, which you will see today. P is equal to 2 is commonly used. P greater than 2 equal to 3, although is a distance metric, not commonly used, but P infinity, Chebyshev is commonly used in machine learning. So what we are mostly worrying about is 1, 2 and infinity. Besides the Hamming distance, which is the 0th norm, which is technically not a Minsky distance, because you're just finding where the bits or the places where they are different, dimensions where they are different. Is everybody clear? So that answers your, is it better, Shivam, today? Your answers your concern. I've searched aggressively to find a case where p greater than 2 is used in real life. I couldn't find it. So everywhere it talks about 1, 2, infinity, 1, 2, infinity. So having said that, p greater than 2, p equal to 3 is a distance metric, but not very commonly used. Is that okay? It answers your concern. There was a question about complex numbers. So yes, distance metrics can be used as complex numbers, nothing stopping from it, but that becomes another part of machine learning. So nothing is stopping you. Basically, you can take a complex number, take its real part and imaginary part, and compute all the distance and work with it. So there is a class of algorithms which have worked with complex numbers. Who asked it? It's not here today. Okay, never mind. So there is a class of things which works, but we are not focusing on it. Is that okay? So that answers the 3 questions about Manhattan, about greater than 3 and complex. Then there was, can I have more reading material? So there's this paper which talks about these distance metrics from a machine learning perspective, which you can read. I've uploaded it here. It talks about many other distances. Do all roads lead to Rome? Studying distance in the context of machine learning. So it talks about many other metrics here. Of course, the very first thing is talks about the metric, the 4 which we have seen. Then it talks about some more properties of them. Eventually it goes to Euclidean Manhattan. It goes to cosine distance, which is also used, Canberra distance. So there are many distances. As you will start using machine learning models, you realize that these are not the only ones we're using. And there are many other types of distances, and then they use these distances in different machine learning models. So you can read about them. Is that okay? So get you bigger idea. Take. So now let's start where we had left. So interaction, lectures, okay. So we'll finish this and then we'll come to that. So where we were going was, why are we studying a lot of these distances? Because we want to define exemplars. Exemplars are representative points of a set of data points. That's what exemplar means, an example. So the very first thing we have seen is that if you want to minimize the square Euclidean distance to a unique point to all the data points, so that will be the mean value. And then so what you could do, let's read this. So it's saying, you may wonder if we drop the square. So instead of the squared Euclidean distance, if we just do the Euclidean distance, what were we doing here? Squared. If we don't do it, then what happens? So it's saying that you may wonder here, it won't be more natural to just minimize the total Euclidean distance. So that the point in that case is called the geometric median. So in the univariate case where it's a function of one variable, it is the median value. Let's say there was only one dimension, there were 10 points. If you minimize the Euclidean distance, not the squared, then it will be the median value. Median value is the equal number of points are above or below, far, distance wise further or away. So we refer to as the geometric median. And if there are in case of many variables, in multivariables case, there is no closed form solution. So that is what it's called. So in certain situations, it makes sense to restrict an exemplar to one of the given data points. So rather than finding a random point in between, you would want to find something which is from within the data set. So example, today we'll do these examples, but one example I give is, let's say they're genomes. Yeah, they are ATGC characters, let's say, Let's say one data point is ATG, AAG, or something, TAG, something like this. And out of these, you want to find which is the representative. These are three sequences of a living organism, let's say plant or human, anyone. So you might want to convert this to numeric first. You may say A is 0, T is 1, G is this, and something. You can still find a mean or a representative, but that may not have enough of value for you. You may want to find which of these represents the three together. So that would be referred to as the medioid. That is a representative data point from within the points rather than a new point. So that is what medioid is. And medioids, again, you can find it by squared 2 norm, or without just 2 norm, without the square, or you can use 1 norm, which is the Manhattan distance. Right? Okay. So this is what it's written, and then it's written the complexity of finding medioids is usually n square. Why n square? Because you will, if there are n data points, you will find distances to all of them and you'll add them. And so, finding with one and then you adding and multiplying, so that will be n square operation. Okay, we'll come about the operations more in today's lecture. We are already 2, okay. So now look at this. So pluses are all the data points in this one. Now you have to find the squared 2 norm centroid mean. So this is the red circle. So you can see this was found by just doing the mean value for all the dimensions, adding them and dividing by the total, and that will give you the point. Then it's saying find the 2 norm without the square, which is the geometric median. So this, when you do that, it turns out to be this. So this is a 2-dimensional case. It is not the median just above and below, because they are multiple dimensions here. If it was 1-dimensional, then it will just be the median value. Then it says find the squared 2 norm medioid. So when you find the medioid, it turns out to be this. It has to be the data point because it is a medioid. When you do without the square, it gives you a different value. And when you do a 1 norm, it gives you another value. So depending on the distance metric you're using, you change your representation or the exemplar. Is that okay? Correct? Yes? Okay. All right. So having said that, okay, so we finish this, we start then today's lecture, which is we are going to do a classifier on this and then do problems on this. So we're doing nearest neighbor classifier. So what is a basic distance based classifier? Let's read it. So the basic linear classifier construct a decision boundary as the perpendicular bisector of the line connecting the two exemplar, one for each class. So in this case, these were my two exemplars. So the very first thing will be to find an exemplar, correct? How you will find whatever norm you want to use, one norm, two norm, infinite norm, whether you want it with square, without square, find a representative. Once you have found the representative, figure out what two classes you want to split this into. You're building a classifier. A classifier is that you're building into, let's say, two classes or three classes, and you want new point to tell which class they belong to, closest to which. So in this one, you draw a line between and draw a perpendicular line, and then one side is shaded gray is one class, the other side is other class. The circles are just showing that all the points here are equally distant from, the exemplar. So if you are here, this would be the circle which is drawn, the pink one. If you are here, it will be the blue circle. If you are here, it will be the gray circle. So every point on this line is equally distant from the two exemplars. So it can belong to either of the class. Is that okay? So let's say you have 3 points. How would you do it? Let's say I had these 3 points. How would I draw the boundary between them? What will I do? Yes. You're talking about this or something else? This only. Tell me, how would you do it? So you will draw a bisector line and draw perpendicular line and same. Correct? So which means that this region is belonging to this class, this region is belonging to this class, this region is belonging to this class. So this is how you are defining it visually. Algorithmically, how you do, you would just see which is the closest and you would just take it to that class. Is that okay? So that is what is shown on the next slide. What is the property of this? These are convex region. What is convex region? Every point should lie between the line. Come, take it. I have to finish some chocolates today. Hey, nobody's answering here. Why? So like he said, what's your name? What, like Ayan just said, you take any 2 points and draw, every point will lie inside the surface, so it's a convex region. Now if we have to draw this is like for 5. What I have done, this is called this comes from the field of computational geometry in computer science. Those who are not scrolling away. Okay, so what we did, these 2 points, perpendicular bisector like this, and then this. These 2 points, draw a line perpendicular, these 2 line, perpendicular, these 2 line, perpendicular, these 2 line, perpendicular. So we are drawing perpendicular lines perpendicular to the line connecting the 2 points for everyone. This and this becomes this line, this and this line, this and this line, this and this line. Then with the interior, this and this and this, this and this. Everybody okay? Now I want somebody to answer from this side. So I want to see. So what are the points? Have I considered all pairs of points? There could be only one answer, yes or no. Everybody on this aisle agrees I have considered all pairs of points? No, you don't answer. It's an answer. अरे जल्दी बताओ भैया, इतना टाइम क्यों लग रहा है? तुम्हारे एडवाइजर तो रियली अपसेट होते होंगे अगर इफ यू आर रिसर्च स्टूडेंट नॉट आंसरिंग. टेल मी, are we covering all pairs or we are not covering all pairs? Yes or no? Who said no? You said? Why? Correct. Wake up. It was just to come. I had to give a chocolate. That's why I was asking somebody there. So what we are not doing, we are not comparing these points, right? The boundary. We are also not comparing these points. The outside one. We are just comparing one with everybody in the center. Yes or no? So there will be another two sets of points which are not visible in the figure, but you have to do a comparison. So technically you can draw this. This is for the sake of explaining it to you. But algorithmically what you will do, if you're given which is I think drawn now. So an alternative way, पढ़ा नहीं जा रहा ना ये scroll पता नहीं क्यों नहीं हो रहा. We'll make it bigger. So an alternative distance way without direct reference to a decision boundary is classify the instant to the class of the nearest exemplar. So you take your data point new one and find a distance to all the exemplars, whichever is the closest, you say it belongs to this class, correct? So that is what we are saying. Okay, so that's one thing. So now let's work out the complexity for this. So now if you want to build a nearest neighbor classifier, you use each training instance as an exemplar. Training instance, for example, I usually take breast cancer or the this plant data as an example. Let's say I've got images which are coming, both normal and abnormal images. Any cancer, breast, thyroid, throat cancer, or liver cancer, or whatever cancer is, the images are there. They may come as normal or abnormal, and then you will train them. That you are trying to make your model, build your model. So you say use every training instance as an exemplar, because you're just starting to build your model. There's no set of data points to find an exemplar. So every training data is an exemplar. So the training time is order n if the dimension of data is 1, and if the dimension of data is d, the training time is n times d. Why? What is training time? Training time is nothing but placing the item in the space. If this is n-dimensional space, this is first data point, I'll place it here, the second I'll place it here. So basically you're touching every data point which is coming. If n data points are coming, its complexity would be n. Because the dimension is d, it becomes n times d, correct? Then you're saying classifying time for one instance is order n. What is classification? I'm trying to just check. Let's say I've got a new instance comes. Now this is I've already set it up. Now a new data point comes. This is what I have trained. There were 3 training data points, it's done. Now I'm getting a new data points to classify it. Now my model is trained. Now a new data point is coming. I have to tell which class. So these are the 3 classes which are already decided. Correct? Now I have to tell which class this new data point belongs to. This is my new data point which is coming. So I have to classify into 3 classes. This is not testing phase that you're putting it in different classes. So how many exemplars will you check with? You'll check with all the 3. Right? So the checking a distance, if this, you'll check with all the 3. These are n. These are 3, so the complexity would be order n. If the dimension, this is d dimension and all of them are same d dimensions, then the distance will have to be checked with every dimension. It will become order n times d. Clear? x1 minus x2 square plus y1 minus y2 square plus z1 minus z2. So you're touching every dimension if it was 3 dimensions, correct? Similarly, if you're classifying m instances, that's m times d. So there is a curse of dimensionality which we'll talk later. Basically all features or all training data is not important. And you may explode it. If you've got a million training points, you don't want to make million classes. So that is called the curse of dimensionality, which we'll see how to tackle. later. But this is how the k nearest neighbor algorithm works. So the k nearest, let's say there were two categories here. I'll show the algorithm first. I'm just telling you the algorithm which you will implement. So it says k nearest neighbors. So rather than, let's say I was already given that there are two classes, and now I am getting a new data point which is coming here. First you will build the two classes. That's the training part which is done. Now when a new data point is coming, it's saying you would not want to compare with all the data points here. One idea could be that you find an exemplar for this, an exemplar for this, and compare. That is one idea. But in the k nearest neighbor, it says that you find the k nearest neighbor, whichever class they are belonging to, and the dominating class you assign it. So that's another way of tackling it. One way was this, where you were looking at all the training data points as exemplar, but this could be too large because there are too many training data points. Another one is that you don't check all of them, you just check selected of them. So in this example, let's say the k was 5. So what it will do, it will check which are the 5 nearest data points. So it checked this. These were my nearest data points. Now let's say which class is dominating. It is more closer to these ones than these ones. So this guy will belong to this class. Is that okay? So this is another way of tackling it. Okay. So that's one. So that is what is written in the k nearest neighbor. The working, select the k number of neighbors, calculate the Euclidean distance of k number of neighbors, take the k nearest as per the Euclidean distance, and then among these k neighbors, count the data points in each category, assign the new data points to the category which the number of neighbors is maximum, and our model is ready. Okay? All right, so this is k nearest neighbor. Now we'll do some problems. So this is first k, yeah, that is a hyperparameter that you're not clear which one will give you the best result. So yeah, that's usually not clear in the k nearest neighbor. Yeah. Come, take this. At least a question came. Come. What's your name? Gaurav, correct. Okay. So now what we'll do is do some problems on these. So it says for the points P1, P2, P3, 4, you are given this values. Says find the distances one place to other when you travel horizontally or vertically in a straight line. So when you travel horizontally or vertically, what is the distance? Manhattan, right? So that is what you find. It's written here. So it's just the Manhattan distance. So what you'll do, you have to given all points. So you have to find every point with everybody else. So you will do P1 with P2, P3, P4. Then you'll do P2 with P3, P4, P3 with P1, P2 is already done, so you'll do with P4, and then this would already been done 642, so you'll just fill it. So you're filling the table, nothing new. Hai na? When you're doing the Euclidean distance, same, it's the square root, and you can fill the values. Everybody okay? So nothing new here. This is, you're given 4 strings, S1, S2, S3, S4, and you have to find the minimum Hamming distance. Can you find it? Work it out on your notebook now in case you're working, just to check that you've understood this. Okay, 1, everybody got it? You just have to see where they're differing, correct? So 0, 1, 1, 0, 1, 1, and then this. Okay. Okay, next one. So this also you can try to do. So they are this. Let me see how many problems we have. This is the last one. Okay. So this problem says you're given this set of 5 data points. Can you write these points and then compute the values? 1 1 2 1 1 3 2 2 3 3 3. Once you have written it down, then for this you have to find the squared 2 norm centroid. So what is the squared 2 norm centroid? Can somebody tell me? So what is the squared 2 norm? You can just do it in your head, no? It's just the mean value 3, 2, 1, 6, 6 and 3, 9 divided by 5, and then 3 to 5 and 8 and 10 divided by 5. So that is what will be the mean value, correct? You don't have to do any computation. So the second it says find not the square 2 norm centroid but find the 2 norm, just this 2 norm centroid. So that would be this guy. Correct? Without the squared. It will not be the mean of the value because it's a 2-dimensional data. So you don't know which one is above or which one is far. If it was 1-dimensional data, it would be the median value. Is that okay? So you would solve this numerically. I have not done it here. So numerically you can solve, which is geometric median. So the value will come, some value will come out. You do the other two. You tell me what is the squared 2 norm median. Either of them you can do, whichever is easier. Find the squared 2 norm medioid or 2 norm medioid. Okay, anybody do? So what will happen? They are turn out to be the same. So for example, you're doing with the k medioids, squared medioids. So what you'll do, you'll take every point and find its distance to every other point, right? So in this one, you will, with x1 it will be 0. With x1 and x2 distance, the Euclidean distance, if you're trying to do, it's saying 2 squared 2 norm. So basically you're finding the square of the Euclidean distance. 2 minus 1, 1 minus 1, so that is 1 square. So you will fill this table value 1. When you're finding between x1 and x3, 1 minus 1 is 0, 3 minus 1 is 2, 2 square, so that will be 4. 4, then you will do x1 with x4. This 2 minus 1, 2 minus 1, 1 square, 2. Then 3 minus 1 is 2 square, 4. 3 minus 1 is 2 square, 4. 4 plus 4, 8. So you will fill this table, 8. Then you fill it for x2. Now x2, x1 is done, so you don't have to do, so you'll fill these 3. x3 with these 2 is done, so you'll this 3. x4, these are done, so this 3, and this is already filled, so this will be this. You add all the distances. Yeah. With the mean point. I'm not sure if that's going to work always. I can't tell that. Maybe it's working in this case. So it's better to do it with every point and add it up. And where you find the minimum value, that will be. I mean, I can't guarantee, I'll have to prove it. So you also try, also check. Come, good, you're thinking. You're thinking with me, that's always better. So everybody okay? So this is the minimum value, and then similarly, if you had to do it without the square, the last one was saying 2 norm medioids without the square, so then it will be with the square root. So you will do with the square roots, and luckily it turns out that the fourth point itself again turns out to be a mediate, but it need not always be true. Is that okay? The last one is just you saying draw the Voronoi tessellation, by now you know, so that's okay. So before I stop, I wanted to go over this basic linear classifier and the k nearest classifier again with you, because I went a little fast on that, I felt. So what we were initially doing, so we started the lecture today with building a basic linear classifier. So the basic linear classifier just said find the exemplars and divide them into 2 parts, whether it's 2 class or it's a 3 class or it's an n class problem. And we said instead of drawing, you can just find which instance is closer and you make that as the classifier. So, and this was nearest neighbor was done later. So let's say there were 3 training samples. So the difference between the linear classifier and the k nearest neighbor is that in the linear classifier, we are assuming that every training data which we are getting is our separate class. They're belonging to separate class. This is an assumption here. So what you did, you made 3 regions. Now whatever is coming, what happened? Fire alarm. So we are about to finish. देखना क्या fire सही में तो नहीं है? So although there are many escape routes, but they are all logged over here. So let's say a new point comes. So let's say it turns out to be closer to this exemplar, so it will go there. A new point comes here, it will go closer to this here. New point comes here, closer to this there. So this is how you'll just keep seeing whichever is the closest exemplar in a simple basic classifier. Alarm ऐसे ये false है. So basically you're not worrying about the new point in the decision making. That is a basic linear classifier. But when you go to the k nearest neighbor classifier, let's say whatever the k value is, the representation of those classes has to be given to you. Like it was given, no, these are 3 different classes, this will be given to you. Now these are 3 different classes. Now a new point comes, let's say this, and it says I'm using 3 k nearest neighbor. So it will check with all the 3. Or if it is using 2 k nearest neighbor, it will check only with this guy and this guy because they are more closer and say this is closer, so I'll become like you. Now when another point comes, it again will say I will check with two nearest neighbors. So let's say the point was coming somewhere here. And I'll say I'll check with two nearest neighbor. It turns out this is close and this is close. So I'll check with two. Oh, I'm closer to this guy. So I will become this. And so forth. So basically the difference between a basic linear classifier and the k nearest neighbor is the new data points which are coming in your k nearest neighbors are helping in the decision making. While in the basic classifier, only the training data or the exemplars were used as the decision maker. This is less commonly used. This is more commonly used. Is that okay? You can use both. It depends on your problem, which one works better, which one works less properly. But usually k nearest neighbor seems to be more popular of the two. Maybe it gives better results in that sense. Because you're using a lot more information to classify. Okay? So now the goal is, tomorrow is your quiz. I think that's why this whole aisle is empty. Is there any computer science 4th year? No, look, no CS 4th year, no. These girls used to come, they are not there. So tomorrow is the quiz and then it will be here only. We'll open the quiz on here, so you'll work it on your notebook. Somebody was asking, can theory questions come? Yes, I can give you a derivation of the dual problem. Apply KKT. I have not formed the problem yet, but it will be doable in 1 hour, which means that you have to study. Like, the goal of the exam, like I said, it to study for the exam will help you remember and understand things better. That's the goal, hai na? So you can't drop anything there. So that's one thing. Second is, if there is a numerical, bring your calculators. Basic computation will be done. Then Thursday, the goal is to, like I said, there will be 2 problems which you will work on, which is these 2 problems. The first is, again, you're finding square medoids and 2 medoids. By now you know this. This one is a real life problem where we are predicting a class and applying the k nearest neighbor. So you can do this. And in the numerical, you will implement k nearest neighbor in Python. One of the most simplest algorithms in machine learning. There's nothing big about it. You just saw, no? You're just checking which are the nearest and bring it to that class. Okay, so then we'll finish. Next week, we'll focus on distance measures again, but rather than do this classification, we'll do clustering, clustering is an unsupervised. Unsupervised because you don't know how many groups you will form it eventually. Classification, at least you know the number of groups that these are the classes you want to put. This is semi-supervised in that sense. So we'll learn about k-means clustering, and that is how we'll finish. Okay, so this is done for today. Thank you.